Hey guys, welcome back. Today in this video, we gonna try to work on tree and implement it with Swift. So we try to understand and review all about tree, and then we will jump to implement it with Swift. Okay, so tree technically it's a data structure that simulate the hierarchical relationship between objects. The structure is just linked natural tree with a tree value and subtree of children and parent node. Hey guys, welcome back. Today in this video, we gonna review tree object in data structure and try to deep understanding Hey guys, welcome back. Today in this video, we gonna try to review tree from data structure. We try to review all details about the tree, and then we will go to implement a generic tree with Swift. Okay, so tree is the data structure and simulate the hierarchical relationship between objects like this, like a tree. So the structure is just like a natural tree with roots and the sub trees, children and parents. So usually we have a root and we have some subtrees. Also we have some children and parents. This is all about the relation in tree. In design pattern with composite design pattern, usually we make a tree. Actually this gonna you following that one as well. So about terminology, so a tree has some properties. A tree can contain a known node, or it can contain the special node called roots with 0 or more subtrees. And every edge of a tree is direct or indirect originated from the root. So this is edge, and this is node, So, and every child has only one parent, but one parent can have many children. So, any child have only one parent, but one parent has many children. If there is only two children left and right, it's going to be binary. But if there's more, then it could be like this. It's could be general tree. So as I said, root, node and edge. Also we have leaf and level. Leaf, it's last node in hierarchical, and which is there's no more child for that. And level is of any node represent the generation of that node. Root is level 0, and while next child is level 1, and go on. So there are more terms about the tree. As we want to have a deep understanding from that, I'm gonna go to any single one, and then we will go through operation, which are very important. And also at the end, I'm gonna go for traversal, ways that we can review a tree. So high of a tree is of a node or root is the length of longest downward path to the to a leaf from the node. So high gonna be length of this one. From we start from here, how many edge we pass is gonna be high. So root high gonna be 0. and leaf gonna be, actually leaf gonna be 0, and roots gonna be high of the whole tree. And depth of node is length of the path to its root. So depth is the length of path to root. So if we start from here to root, it's going to be depth, and from this to this is going to be up to down, it's going to be high, and from this going to be depth. So depth of roots is 0, but high of root is high of the whole tree, and the leaf is exactly opposite side. And if our tree is empty, then high gonna be -1. Okay, internal node. Also we call internal node inner node, or in node as a shorthand, or even branch node. Is any node of tree that has child's node. So any node that has a child is internal. And external does not have a child, like leaf is a child, external. Subtree. So any if I want to go through definition of a tree, consists of a node, any when we go down from root, then we have one subtree. When we go down from that one parent to child, again we will have another subtree. So could like exact tree. Neighbor, parents or child are neighbor. So when we say neighbor, parents or child, they are neighbor for each other. And ancestor, a node reachable by repeated proceeding from child to parent. So ancestor is a node that is a node that reachable by repeating procedure from child to parent, and descendant, a node reachable by repeating procedure from parent to child. So from child to parent, ancestor. From from parent to child is descendant. Branch node or inner node, we said already. Degree. For a given node, it is its number of children. A leaf has necessary degree 0. Degree is for a given node, its number of children. So excuse me. So for so it's said that degree of leaf is 0 because there's no children, but degree of roots are gonna be how many. Or for example, degree is 3, where this degree is 0, this is degree is 1, this is degree is 2. Yeah. And degree of a tree, the degree of a tree is maximum degree of a node. It's going to be degree of that tree. And distance, the number of edge along the shortest path between two nodes is distance. So if we count number of edge, this is going to be 3, for example, distance between 2. But shortest path is important. And this the level, as we already spoke, is the number of edge along unique path between that root and node, and with the number of node in one level. So with it's the number of node in one level. So if we go on this level, which they are all one level, so the width of this level gonna be 4. And let's go and breeds. The number of levels gonna be breeds, and the forest, if we have some disjoint tree, number of them, it's gonna be forest. And the ordered tree, a rooted tree in which an ordering is specified from children of each vertex. It's going to be ordered tree, and size of tree is number of node in tree. So if we count number of nodes, it's going to be size of that tree. Okay, So now let's go through and operations. So operations, like a class that we have property and then we have some behavior, some method. Operation are those that give us some feature to deal with this tree. So insert, let us to insert one element in our tree. Search, let us to search an element in a tree. And also for we have traverse, because tree to have it in the computer programming, we need to traverse it and convert it to an array or reverse. So for traverse, we have two ways. We have depth first traverse, which means that traverse a tree in children way, so manner. So if we go for traverse this tree and we go by this way, and then we go through this one and this one, then again this one, it's gonna be tree. So it's gonna be traversed by breadth. Actually it's going to be depth first traverse. And for this we have three way: pre-order, in order, and post order. For pre-order traverse a tree in a pre-order manner from it's going to be root, then left, and then right. And for in order it's going to be left, root, and right. Let me show you. So so root, left, and right. It is going to be pre-order, but for in order it's going to be left, root, and right. So it's going to be like this: left, root, and right. So we start from here: left, root, and right, left, root, and right. So this is going to be traverse of in order. And post order traverse, actually you need to know that this traverse are mostly only for in pre-order. It's only for binary, that we have only left and right. And post order traverse tree in means that left, right, and root. So left, right, and root. So this is going to be post order. You need to know this when you want to deal with a binary tree. Other than that, depth first tree is gonna go by children way. And breadth first or level order traverse, we go by level by level. So like this one, then level next level. So you usually go from left, right, then next level, then next level, then next level. This is level order or breadth first order. Okay, so that's it for all about the three terms and operations, but I want to before jump to implementation, I want to go over some important tree, and then later for each of them I'm gonna make a video and we will talk about details as well. So we have more, not only 8 times, we have much more, but I'll go through this one. So general tree is number one. General tree is a tree that there are no constraint on hierarchy or structure, follow property of a tree, and a node can have any number of children like this. And usually we use this for hierarchy data structure as a folder structure, that we can have more, but there are some other functionality for that. Binary tree: a binary tree is a tree structure where the following property can be found: properties, and this property gonna be follow property of tree. A node can have at most 2 digits child nodes, so left and right. And these two child nodes are known as a left child and right child, and they will have only, as it's part of a tree property, they will have only one parent. Usage: so usage by compiler to build a syntax tree, usage to implement expression parsers and expression solver, used to store router table in routers. So router table in routers use, and much more. So binary search tree is more constrained extent of binary tree properties. Followed properties of binary search tree, so followed properties binary tree, and then has a unique property known as a binary search tree property. This property states that the value or key of the left child of given node should be less than or equal to the parent's value, and the value of the right child should be greater than or equal the parent value. So this is when this is our node value, this should be less or equal right value and bigger and equal left value. This is then this is going to be binary search. So for binary search, if I want to go through some use to implement simple sorting algorithm, can be used as priority queue, which will very important subject in tree and even data structure used in many search applications where data are constantly entering and leveling. So when our data has constantly coming and leveled. AVL tree. AVL tree is a self-balancing binary search. So it is the binary search tree, and this is the first tree introduced which automatically balance itself it's high. So it's not only balance, it's high also by some constraint gonna balance itself. So follow property of binary search, self-balancing. So each node store a value called a balance factor. So each node has a balance factor, and which is different in height between its left subtree and right subtree. All the nodes high between left and right, all the nodes must have a balance factor -1, 0, or 1. After performing insertion or deleting if there is at least one node, that node not have a balance factor of -0 and 1, then rotation should be performed to balance 3, and you can read more about that later in our video. So usage use in a situation where frequently insertion are involved. So we have data that frequently coming, so we use AVL because it's gonna balance itself and keep it balanced for when we need it. So use in memory management subsystem of Linux kernel and to search memory regions of process during preemption. And other one of tree gonna is a red-black tree. A red-black tree is a self-balancing binary search tree where each node has a color, red or black. The colors of the nodes are used to make sure that tree remain approximately balanced during insertion and deletion. So this is the second one that do self-balancing. So property, follow property binary search, self-balancing. Each node is either red or black. The root is black, sometimes omitted. All levels, denotes or nils are black. If a node is red, then both its child are black. So every path from a given node to any of its leaf nodes must go through the same number of black nodes. So these are constraints we will go over later, but a node can have at most 2 children. It's a binary. So usage as a base data structure used in computational geometry and used in completely fair scheduler used in current Linux kernel and used in EPOL system called implementation of Linux kernel. So this is the other one. We have I have gonna go through three more. So splay tree is a self-balancing binary search tree. Property follow property of binary search tree and self-balancing, but with different constraints. So recently access element are quick to access again. Recently, this is good for we will go over that, for implementing cache, garbage collection, and data compression. After performing a search, insert, or delete, a splay tree perform an action called splaying, where the tree is rearranged using rotation, so the particular element is placed at the roof of the tree. So here we go. This one, then it's gonna go to the roof. So usually we will have the latest on top. And trip, the name derived from tree and heap. Yeah, I just said that it's close to heap. So is a binary search tree property. Each node has two values, a key and a parity. So the key follow the binary search tree property, and the parities, which are a random value, follow the heap property. So it's gonna be both heap and tree. It's use maintain authorization certificate in public key crypto system, and they can be used to perform fast set operation. And finally, for this video, I'm gonna go through the last one, B-tree. B-tree is a self-balancing search tree and contain multiple nodes which keep data in a store order. Each node has two or more children and consists of multiple keys. So properties: 1. Every node X has the following: x.n, x.key, x.leaf. The number of key, the key is stored in the ascending order, and where is a leaf or node. Every node X has x.n plus 1 children. The key, the x.key, separate the range of keys storing in each subtree. All the levels have the same depth, which is the tree high, and the node have lower and upper bounds on number of key that can be stored here. We consider a value t bigger than equal to called minimum degree for balancing factor of B3. The root must have at least one key, and every other node must have at least t minus 1, and key and most 2t minus 1 keys. Hence every node will have at least t children and most 2t children. We say node is full if it has 2t minus 1 keys. So I know it's a little bit confusion because it's a lots of constraint, but it's useful for, it's going to be something like this. We will go over a separate video for this as well. And so usage in database indexing to speed up the search, and use in file system to implement directories. So this is all for theory. Then we will go for implementation. Okay, and now we are going to implement three data structures. So three data structure. Okay, so we start with public class. We name it tree node. Also, we make it generic from type of T, and so inside this we create public variable, but with value of T. So this is value of the node. Also I create public weak parent which is type of tree node. I make it optional and weak because and to avoid memory leak. So also we will create public var child. So we create parents as a weak, then child don't need to be. And child, we say each, in definition we said that each node can have only one parent, can have, not must have, and can have how many child. So I make an array of 3 nodes, and I put 2 parentheses to give it at least to be empty at the beginning. So for initial, so init value from type of t, I just say self dot value equal value. So this is gonna be our initializer. Okay, so now we need public this one function add child. You can put insert add child, so I put add child. Okay, and I make it broadcast node, so when I call it I don't need to mention parameter name. Again, 3 node of t. So inside this I just say children dot append new element of 3 node. Yes, so node, and then node dot parent will be self. So we add a child, we say okay, our children gonna be this node, but parent gonna be self vr because it is we're adding a child. Okay, so this is done. Just we got some error, I think. So parent, yes, so why we get error here, we need to think about it. Here expected declaration 3 node, so parent, oh, you know what I missed var here, so this is gonna go as well. Okay, yeah. So yeah, let's go and to second part. So now I make an extension for that, for my 3 node, and this extension I make it custom string convertible. So this description help us to add description. So when we want to print this node, our function know how to deal with that. So we have planned for that actually. So I just say yes, it's gonna be a string. So var s equal /, so I convert my value to a string, printable string, and I say if no children, so if there are no children, no, sorry, if there were children, then s plus equal, so I put one curly parenthesis pros children dot map by this condition. So description, then I just add join, but for joint I add separator, this, and at the end I'm gonna add so it said yeah, I'm gonna add a curly parentheses. Okay, so I made some mistake here, I think because this plus is stick to this, and same here. So by this way we can create a description, but we need to make sure to have return, because return gonna be a string. So instead of s I make it str. I don't like one character variables. Okay, so now we have we can print our array. Also I'm gonna write another extension for tree node where my type is equitable. So here I just say public function search. So when we want to search, we need to be able to compare, yeah? So search my value from type of T, obviously, then return tree node, but it could be optional because maybe we find something, maybe we cannot find. So if value must equal self dot value, okay, so value, so actually it's value if it was equal self, then we gonna say okay, what to do. Let me first make sure this value, fix this value, yeah, is equal value. Then I want you to return self, is base case, yeah, and then I'm gonna for child in child, so I iterate inside children, and here I just say if let found, if you find it, find what? Child, search value value. If you find this, then you can return. Fine, so it's recursive, yes, and if not, return nil. So also complexity is O notation n, because we gonna check any single node inside our tree to search. It's worst case actually. Okay, so now we gonna go for traverse. So I write extension for tree node, and so in this extension I'm gonna write traverse depth first, also traverse level first. Okay, so to do this I write a function. I name this function for each depth first. So this function get parameter visit, which is the closure of tree node that return void and nothing to return. So this here gonna be implementation. Also I make another function. This one gonna be each level first. Okay, so for each depth first, we will go by depth. So how we do that? First of all, we said, okay, visit what? Visit self. So we start from visit self, and then we say, okay, in our children, go and iterate for each okay, and my for each I just open and close parentheses, and inside here I just say okay, from first operation go and do for each first, and here first what? Visit, and this guy gonna be self. That's how easy we can iterate depth first, and just say recursion here to just remind. This is recursion. For the other one, again visit self, and I create variable q. I need a q definition, so I already made that. So let me go. So is this q gonna be from type of tree node? Okay, so just here I defined the tree already, because we will have a video for that. You can check it over there. So from this queue, what I do with that, so I'm just gonna go, okay, my children dot for each what I want my no, not this queue, my queue dot in nq which element? Element number 1. So I do that like this, and after I'm gonna go for while loop. So just okay, while let node equal q dot dq. So what I want to do, as long as my queue, so first I put everything in queue and then I'm gonna dequeue it one by one. So I'm gonna visit node, and then in each node dot children dot for each q dot enq first argument. So yeah, that's it. I just have some error here. It said a value of, it has no member of for each. Oh, I missed one R. Okay, plus this two way for traverse, I make another way for printing graph of our tree by the name of yeah, I make this function print tree from type of tree. So in parameter just say node of t, also node info dot add escaping, and escaping disclosure. This means that if this could take time to finish, don't keep this, don't stop this function, continue, and then later you have time to finish this function. So this closure actually, this main function, so a string and array of t. So and we do not return anything here. So let's go for implementation. Inside this again I create a function. This function gonna be lines, which is underline a node from type of t, and underline node indent from type of string, which default value nothing. Also I'm gonna add one child indent, this one from type of a string as well, equal nothing by default, but here we're gonna return an array of string. Okay, so in this function what I do, I just say, okay, let's label, couple label, and children equal node info with value a node. Then return array of node indent plus label. But not only this, plus children dot enumerated, so enumerated for me, and then map it by this way. So parentheses 0 smaller than children dot count -1 and second. Also flat map it for me, so flat map by this way. The first argument, if line lines of the second actually argument, and okay, here I need to put some special character. I'll put it later and then show you, review with you. So and this line with a space. So if this option was this, otherwise go and put lines number 1 with this and just only one space. So this one, it's gonna be, you know, this line and this, and this one is gonna be this line and sorry, and this. Okay, but not finished yet. Again, I'm gonna map it with this condition: children plus $0. Okay, at the end of all of this, so end of this function, technically, yes, I want to print lines of node dot joined separator with slash and just goes to next line. So I think this is the one, but something missing here, that's why I got this error. So children, it's not children, it's children indent. That type was wrong. I believe yeah, this is completed. So what I'm gonna do, I'm gonna take this to playground, lead code playground. So let me copy this and I'll go to my lead code playground, paste it here, and I try to run it. I shouldn't get error, then I can write codes that call this. Yeah, I didn't get any error, so I come back here. So to speed this up, I typed this already, and so I come here, and on top of this implementation that we did together, I'm gonna, what I do, first of all I create a tree from tree node with value beverages, and then hot node with tree value of hot, and so on, tea node, coffee, chocolate, black tea, green tea, soda node, milk node, and then I'm gonna add this. So from tree I'm gonna add child hot node, cold node, and for hot node I add tea, coffee, chocolate, and for cold I'm gonna do this, and then I try to print this in two way of print tree, and also printing in depth first and level first. Okay, so if we run it, we should see print, get error in line 53, calling for each, yeah, this one. So probably I have typo in this for each. Yes, I think I missed one C. So yes, here you are. So what we did, so we made this tree, and then here we gonna print this. So when we print this, it's gonna print it in this way. So start from new, which is top, and then actually these are prints. These are print that we did. Print search for cocoa, search for chai, and for bubbly, which are new, but it's to return for us. So found it, and show that to us. And then I print my my tree, and you will see some visual as a graph here. So this is the function that we did. Let me go over the function, just review together what we did here. Here we go in the print tree. So we print node by node, and here in last portion I just said if this one was true, then put this line for me, otherwise put this line for me, which is the last one. So yeah, now just let me make this fix as well, because I'm gonna put this, I'm gonna put this in GitHub for you guys to be able to get idea about that. So yes, here you are, and also we have depth first, print for that, traverse for that, and level first. So you will see level by level, gonna be like this: beverage, hot, cold, and tea. Here we go, beverage, hot, cold, and then tea, and coffee, and continue. And depth first gonna be beverage, hot, tea, black, green. Here we go, beverage, hot, tea, black, green, then chai and coffee, and so on. So this gonna be implementation for 3 almost complete. They include add, search. We can add, delete and some more later. But yeah, that's it for this video today. I hope you like this, and if you like it, please make sure to give it thumbs up, and don't forget to be subscribed and for other videos coming every week. Have a good one. Bye bye.